Thank you so much, everybody. It's wonderful to be here. My name is Naeem Merchant. I'm the Executive Director of Carbon Removal Canada, a new policy initiative focused on the rapid and responsible scale-up of carbon removal in Canada. And frankly, I'm humbled to be on stage today moderating a panel with this group of experts. Unfortunately, Dr. Shruti Talati couldn't join us today, but what we have here today is a group of experts that have been at the forefront of leading the development of direct air capture for decades, really. And what we wanted to talk about today was the sustainable future of direct air capture, its deployment, and how to measure it. Now, a lot of the conversations that I have about direct air capture are focused on what's possible today. What are the costs today? What are the technology limitations today, right? And this, I think we decided collectively, should be a conversation about the future. What are the possibilities for direct air capture in the years ahead? And what are the risks? And so that's what we're going to try to talk about and unpack in our first panel. I want to thank Columbia University, RMI, the Direct Air Capture Coalition, Breakthrough Energy for making this event possible, and look forward to a fruitful discussion on what we mean by sustainable development in DAC and what that future looks like. So without further delay, I'll introduce our panelists and then we'll get started. We'll have Dr. Peter Eisenberger, the co-founder of Global Thermostat, as well as the Coast Institute, and a professor of Earth and Environmental Studies here at Columbia University. Dr. Klaus Lackner, the founding director of the Center for Negative Carbon Emissions and a professor at Arizona State University, and Dr. Peter Psarras, research assistant professor at the University of Pennsylvania. Thank you so much for being here and participating on this panel. Now, when we all kind of got together on a call to talk about this panel, it seemed like there were a lot of really passionate takes about what we should talk about and what the topic of this panel really meant to people. And so we decided we'd just start off with some opening remarks and to hear what folks had to say about the topic that we're going to talk about here. And then we'll shift into giving folks an opportunity on the panel to respond to those opening remarks. And then I've got some prepared questions that we'll get into. So why don't we start with you, Dr. Eisenberger.
Thank you. First of all, I'd like to also thank the DAC Coalition for holding this meeting, and also want to point out that my son has played this, and Jason have significantly played a big role in bringing us all together and helping us have this platform to have the much-needed dialogue between us. I should point out as well that the idea for this coalition emerged about 2 or 3 years ago in a workshop that Jason and Nicholas were part of, and I'm so glad to see it be in fruition. When I came to Columbia in 1996 as a founding director of the Earth Institute and director of the Lamont Doherty Earth Observatory, DAC was not part of the discussion. It was, instead we went through phases, various paradigms to address climate change, starting from climate denial to clean coal, which is an oxymoron if I ever heard of it, and to natural gas and renewables, and now net zero. What I believe is that because we've taken so long through these paradigms and have not yet mounted a significant mobilization effort, and in that time, the amount needed to be removed, as Klaus will point out, has grown, and the time we have to remove it has shortened. And that has what has produced the crisis that my son Nicholas and Jason talked about in the introduction. So I believe we have to have a new paradigm. And I believe that paradigm is something I call the renewable energy and materials economy. It regards carbon dioxide not as a pollutant, not to be stuck underground, but as the building block for a new economy, which when combined with hydrogen from electrolysis, all powered by renewable energy, can produce all the liquid fuels and all the solid hydrocarbons like carbon fiber and aggregate and various other products that we need. And this economy is clearly sustainable. It mimics photosynthesis, what nature does, and it has a closed cycle for the energy component and a sequestration component in the materials. I believe that this approach will remove a big problem that has divided us. That is, who's going to pay for carbon removal? In this approach, this way of making and monetizing the carbon as a valuable product, the discussion instead is going to be who's going to get the benefit from the economic growth and increased equity that this approach of this type of economy, this delocalized economy, can bring to the planet. So it also has, it has that feature because there's a positive feedback loop between increased wealth generation and increased energy, climate change protection, and equity. And so those positive feedback loops mean that rather than working against the tide and deciding who's going to pay for it, we all can work together to get the benefits and make sure they're equitably distributed. Now, the second thing I believe we have to do is we have to decide, and my son sort of introduced this in the beginning, what he called radical collaboration. I believe the time has come that we need to think about how we can mobilize now, or at least provide a program, get a program of trillions in 2025, by 2027, and not billions. And we have to work towards that goal, and that government, that money has to come primarily from the government, because this is too big a task for the private economy to do. Now, how do we do this? Well, we can take a lesson from the Manhattan Project. What they did is they brought all the experts together and they made some hard choices. What's the best way to proceed? How do we guide our R&D program? And they, physicists at that time had all sorts of ideas, but they eventually disciplined themselves to come up with a few and the path forward. I think that's the task before us. The time has come. It's nice to have all this different, disparate efforts going on. They're all, I'm sure, well-intentioned and will accomplish stuff. However, we don't have the time, right? FDR, in response to World War II, increased the federal budget by a factor of 9 in 1 year. And so we have to do our part. We have to present to the government officials an agenda that is focused, that makes hard choices. And once that agenda is agreed to, we each have to, like the Ukrainians, stop what we're doing and contribute our expertise to the chosen path. If we don't do it, nobody will. And therefore, I really hope out of this conference we can get some consensus of how to make these hard choices. And I would suggest, though I understand it may be challenging, that the best approach may be to use the DAC coalition to try to organize such an attempt to make these hard choices. Again, I want to end by making an analogy between the proverbial frog and the boiling water. For all these past years, except for the last 2 or 3, we've been basically in that pot and not acknowledging that there's any reason to get out of it. In the last 2 or 3 years, we can be characterized as thrashing around in that pot, but no coherent effort and no way to get out of it unless we have a coherent effort, and we make that coherent effort now. I want you to know that this is what I recommend, and I'm also doing something myself personally. I have changed my affiliation to work for the Equitable Climate Innovation Institute, and as part of that institute, we're collaborating with the Great Rift Rally to try to do a demonstration project of REME in Kenya. And so I hope all of you will find ways to do your part, and thank you very much for this opportunity to address you.
Klaus?
Thanks for having me here, and it's a great time to be back at Columbia. I've been in this area of work since the early 1990s, so some 30 years ago. And I think the brutal climate math, which was mentioned, was actually clear after the Rio Agreement, where we casually agreed that we need to stop the greenhouse gases in the atmosphere at a level that is not harmful. Because even then you could see that means we have to go to zero in carbon dioxide. So it was only a question, when do we hit the ceiling? And that ceiling, by the way, has come down. Back then people said 500, 550 is a perfectly fine number. Nobody says that anymore. 450 is already more than 1.5 degrees, and we want to stop. But so you can then, even then you could see it was 25 gigatons a year then, it's 40 gigatons of CO2 a year now. We are going up by roughly 2% a year still. We are still accelerating. We come out of COVID still on the gas pedal. So we have to figure out how to get there. Now, direct air capture is a carbon dioxide removal technology, and I think it will play a big role in the overall discussion. Since we are too late, since we live in an overshoot and have gone over it, I think one of the big roles DAC and CDR in general will have to play is to pull things back down. And just to give you a perspective, if we are overshot by 100 ppm and we'd like to fix this in the course of 40 years, we are talking 40 gigatons a year just dedicated to this problem. Never mind whether we manage to phase out fossil fuels or not. If we are 100 ppm above where we'd like to end up, we have 40 years of current emissions going in reverse. We have to pull that much back every year. So I do think that direct air capture can be a major, major player in this. It is still too expensive, probably by an order of magnitude, but it can come down in price, just like photovoltaics has come down. I think it has a big advantage that it's inherently scalable. You can put as many units out as you like. And one of the things which got me started was the observation that the direct air capture device, which stands in the wind and collects CO2, is actually much smaller than the windmill, which has the same amount of carbon impact by not emitting it in the first place. So from that perspective, this looked interesting. The other part is that the thermodynamics, no matter how you look at it, is not all that bad, because the energy it takes is around 22 kilojoules per mole, or roughly half a gigajoule to get to 1 atmosphere. And by the time you are at pressurized CO2, your thermodynamic requirement is around 220 kilowatt hours per ton. That is affordable. Now, we are right now an order of magnitude beyond that, but that also tells you that we can learn, that there's room to get the costs down and make it happen. So I think it will be affordable. But I think the real advantage of direct air capture is that it takes every excuse away of saying, we don't know how to deal with this problem, we just have to muddle along, and you can't help it. And you have seen this going on in the discussion over and over. You see it in nice things in Europe. You say, okay, the power plants, which have some idea of how to deal with it, they have to do it. But people driving cars, we can exempt, and they have done this now for decades. We are gradually getting around to that you cannot do it, but direct air capture really helps there, because it tells you you don't have to exempt anybody. You can think of it, and I think there is where Peter and I have a slight disagreement. You first and foremost have to say this is a waste management issue. You are not allowed to dump that CO2 into the atmosphere. And direct air capture guarantees that you have a cleanup. You also have an insurance if you lose it after you stored it. What you really need is a requirement that if you dig up a ton of carbon, you have to put a ton of carbon away permanently and safely and forever. And forever means tens of thousands of years. Now, you can lose it again, you can on purpose lose it again, but then you are obligated to get it back. If we do all of that, we can move forward with a certificate of sequestration, and then we can create negative emissions by saying Western societies, rich countries, have overspent their budget. We bought a pizza with 12 people, and 2 of them ate 11 slices. And now they argue who gets the last slice and how much they get from it. We have to get out of that mode, and we have direct air capture can help us. And then, yes, Peter is absolutely right. We can try to figure out of mining the carbon from the atmosphere and take it back to do useful things with it. At that scale, we'll likely make fuels, but maybe we also make all sorts of carbon products which are worthwhile having. And then we can close the loop that way. And I think direct air capture will play in that game just as well. And in 100 years from now, we will have solved this problem of climate change. But we still may want liquid fuels, and we get them from photovoltaic energy. And here is the last thing I want to point out. If you look at renewable energy, which is inherently intermittent, squeezing it into the grid is very, very hard. If you have the ability of storing it chemically and then distributing it to where it is needed, you really have a leg up in the game. And again, this is a place where direct air capture plays a very big role. So I'm looking forward that it can help solve the problem. It is not the only player. There will be plenty of others, and it has to compete in this game. But we have to try out many different things, and we better try out things which grow fast, because that's what we need. And I'm a little skeptical that if we think of these as billion-dollar individual investments, that we take the risks we need to take. Mass production in many ways has won the game, and I would point out that a car engine, kilowatt for kilowatt, is 100 times cheaper than a power plant. And so therefore, high modularity is likely to be a good way forward in all of this. And thanks for your attention.
Thank you. Pete?
Thanks, Klaus and Peter. And what an exciting time to be in direct air capture. The amount of movement over the last 5 years, I don't think anybody in the room could have expected where we are today. I think direct air capture is a terrible idea. It's a shame that we have to do it, but we have to do it, right? And want to get that out of the way. And I'm glad we set the stage with comments, that the success of direct air capture largely will rest on how successfully you can decarbonize economy-wide. The success of direct air capture is going to largely rest on not asking it to do too much. There's what we are asked to do here, and I think a lot of what the conversations will weave into the next 2 days. It's a very, very challenging problem for so many reasons. I think it's challenging because we still don't know what this looks like. We're trying to understand an industry that is in its infancy. There was a wonderful Rhodium Group analysis that came out this week, a second of its kind to talk about job creation. And I had to chuckle when it says we still don't have a large-scale commercial direct air capture plant to base these numbers on, right? And so we're still studying this. That is a benefit. So many eyes on this, trying to steer this right from the start. And I think we have an opportunity to do that. The immense scale that we're after, this is even minimal if we think about a gigaton, and I think my panelists agree that that's way too low. You're still looking at an orca an hour every hour from here to 2050, and hopefully we're not measuring in orcas soon, but that's still just an immense scale, and that immense scale means new challenges, solutions that look great at the bench top, even look great on paper now, may fail when we start to push this to that mega and gigaton scale where we're stressing supply chains and we're stressing our energy infrastructure, et cetera. The tremendous infusion of capital that is required to do that and to achieve that. And so we have to take a moment, and I don't think the challenge here today is to define the principles of high quality removal that direct air capture can hit on, and that how we want this trajectory to proceed. It's how can we remain uncompromising on those principles as we try to hit that scale. And I think that's the opportunity that's in front of us today and through this conference. I'm so encouraged to see that this is a multidisciplinary effort, that's recognized. I'm excited to see the structure of the conference and the social and the economic and political disciplines all coming together to solve this together and collaborate. So with that, thank you.
One theme that kind of came up in some of the opening remarks that felt a bit of a variation in terms of our visions for direct air capture going into the future is this idea that we treat carbon as a product in a renewable energy material economy, or we treat it as a waste product. Klaus, Klaus, can you maybe comment a little bit on kind of Peter's vision for the renewable energy material economy and how that comports with how you're thinking about the important obligation to take back carbon that's been emitted?
They are not at all contradictory, but do it in sequence. The first step is we have, since the beginning of the Industrial Revolution, we have decided that it's a great thing to get carbon out of the ground. We got it not because we wanted carbon, we got it because we wanted energy. And so today we end up with 40 gigatons of CO2 we don't really know what to do with. And that, by perspective, is more than sand and aggregate. So this is a huge, huge output. And so far we said we don't know what to do with it. The air is just a fine place to put it. So now we need to change this. This is where the waste management comes in. The waste management approach now says you have to pay for it. And the way I would do it is I would hold the fossil fuel industry from today on responsible for every ton coming out of the ground. You better show a certificate of sequestration. And since we don't know how to do this right now, we give you time to realize that certificate, but not an infinite amount of time. And the liability should start today and not sometime in the future. Now, that will put a price on carbon. The next part then is, do we really want to get rid of it? Can we actually use it? And this is where Peter comes in, and he says, you know, we could do useful things with that. And I would argue the very first thing we can do is make liquid fuels out of it. Then we don't need fossil carbon from the ground. And I would argue if we really end up with 40 gigatons of CO2 that have to be put away every year, the price of storage will stay high. And the reason it will stay high is the same reason that oil went from about $11 in 1998 to $147 in 2007 or 8, because there was a shortage in the supply chains, not because we ran out of oil. And if you tell me that we need to put 1,500 gigatons away of carbon dioxide, that price will be high, and therefore renewable energies entering into this game will have a real leg up in their story because they both will need DAC, but one of them will need storage and the other one will need chemical conversion, and that's how this will come together.
So Klaus and I have had this discussion for quite some time.
Yes.
And my view is the following. As I said, Klaus and I don't disagree factually, but the question is, how do you package this? How do you communicate it to get the response that we need? And I'm saying the minute you bring up waste product, it brings in people's mind who's going to pay for that waste product. And that starts right away and has blocked the global accord needed in the IPCC because they're debating who should pay for it. On the other hand, if you have a paradigm that says, you know, CO2 is a valuable molecule, together with hydrogen from water, we can have a new industrial revolution that's going to create jobs, and it's going to be done in a way because it can be modularized and delocalized in a way that benefits countries uniformly because everybody has water, air, and sun, or wind, or hydro, or geothermal. And so it's a much more equitable economy in the first place. And so by inspiring the fact that this is a wealth generation thing, you can go to any government in the world and get support from it because they're now vying to have this economic growth occur within their borders, and they're competing with each other to get that done. And one final comment is there's no way, even though I say REMI and making it valuable, but it's really, that's one aspect of it, but the most important aspect of it is to get the governments to buy in, because there's no way that this problem can be addressed unless the government and the sovereign funds are committed to do it. I pointed out that FDR increased the U.S. budget by a factor of 9 to respond to World War II. That gives you some idea of the dramatic change that has to be made in all our lives and everything we do if we're going to face this. And I guess one final comment is, you know, we're having this discussion in New York, but in fact, we have to find a way to convince the poor people, the people who don't have their basic needs met, or the people struggling, that this is a change that's going to help them. Otherwise, we'll put their governments into some really serious bind of how to make the necessary sacrifice that's going to be required to protect the whole. So that's why I believe this new paradigm of viewing CO2 as a valuable molecule and building an economy around it, I'm not disagreeing that if you want to make sequestrate in certain circumstances, but as the paradigm for presenting it to the policymakers and the funders, I think it's a better way to go.
I'll add, I've been a champion of CO2U. It's how I cut my teeth in this industry, that type of research. There's certainly, we can't talk about this without talking about energy, and we can't talk about this without talking about cost parity, right, for these solutions. And when I think about thought through this, there are lots of very bright people thinking about how to convert CO2 into useful products. They're not all good ideas. Many of them are, and I will say that when there are opportunities for that to be the least cost or best cost option, or least impactful option, then I think we ought to consider it. But every time you put CO2 into a product, you are passing on the opportunity to put that carbon away. And I think we have to take that into consideration. I do like the waste analogy when I think about putting one trash bin out to the curb every Sunday. Per capita U.S. at least that's 22 bins every Sunday, and trying to bring that at least in terms of a kind of a social image.
I'll let Klaus
in some ways, I'm firmly on both sides of this fence, right? I'm working with a seller here, a company in town, a former student of mine, Eric Dahlgren, founded it, and I'm on their board, and their goal is to make liquid fuels out of CO2 they took from the air. So I'm clearly in that camp, right? On the other hand, I work with Carbon Collect at Arizona State University, where we are collecting CO2 for the purpose of disposal mainly, but I think they'll give it to anybody. But Aircela is built around the concept that you make fuel, and it's designed that way. On the other hand, I would also argue we are looking too much at the high price tag, which may not be as high as people think. And I give you an example. If you take 10 gigatons a year, which is a pretty hefty chunk, at $100 a ton, and I do think prices will come down to that kind of level in fairly short order. If not, we are betting on the wrong horse. So, but if you are at $100 a ton at times 10 gigatons a year, you're talking $1 trillion a year of cost of operation, of revenue in that process. I would point out that there's another industry which some 30 years ago was in its infancy. And even in 20 years ago, you could say it was very small. Think Apple, think Google, think Microsoft, and Amazon. If I add them up, they have a revenue of $1.4 trillion a year right now. And this is paid for because we like to pay for it. As a matter of fact, a large fraction of this is advertising, right? So we can get to that scale if we choose to. The barrel equivalent of having a synthetic barrel, the CO2 in that at $100 is about $40 a barrel. Prices of oil have gone up and down by far more than that in the last 25 years, and the economy has perfectly well absorbed that. So we can do it if we choose to, but we do need, and there Peter is absolutely right, we need a regulatory framework which forces that it is done, because this one needs pull. It needs the push, I should say, from regulations which say you must do it. And I'm not convinced that we couldn't do you must do it if we simply say you need a certificate of sequestration if you want to dig up a ton of carbon.
Do you want to close us out on this topic?
Yeah. Yep. So, first of all, this Peter.
Mike.
Pete. What? Yeah. So, you said you favor the waste because there was no way to sequester the carbon. But I point out to you, and I think I even sent you the paper, that I did an analysis that shows there's enough storage capacity in aggregate and carbon fiber as in the next 20 years, so that we can sequester, in my opinion, all we have to remove. However, whether that's true or not, because that's in the future, what I want to point out is that the current pricing for CO2 is very inhomogeneous. It goes from over couple $1,000 in island states and in Africa, and for use for medicine, transport, and cold chain applications. And so there's plenty of opportunity, right, to convert it into valuable products now, right, because one can make a profit now. And again, showing that, demonstrating to each country that bringing DAC into the country, combining it with renewable energy and hydrogen electrolysis, one can generate jobs and wealth, that's going to motivate them to unzip their wallets and support the scaling effort needed. It's never going to happen in the time needed to decide who's going to pay for the waste. And anything that costs people money, unfortunately, right, at this stage, is bound to be very difficult to do politically in any time needed. And so what I'm strongly recommending we think about is that we get the ball rolling by each of us finding ways to demonstrate that using CO2 as a valuable molecule, one can make money, and do those demonstrations, and then find a way, as I said before, to come together and find the best approach to scale DAC and to scale the associated technologies that are needed to turn it into a valuable product and stimulate the economy. That's what happened in the Manhattan Project. It wasn't just what happened in Albuquerque. Factories and manufacturers around the globe, around the United States, were commissioned to build all the supply chains to support the Manhattan Project. That's what's needed here, right? And as I said, there's no other organization in the world like this organization, and it has all the parties at the table that need to make these tough choices. And I really strongly encourage that one think about it, or you have some way of deliberating how that can be done without necessarily the DAC Coalition doing it, but they could provide some way of creating an independent group that can make the tough choices needed.
Thank you. Pete, I want to go back to you for a second. You know, we're thinking about large scales of direct air capture deployment, and the topic of this panel is the sustainable deployment of direct air capture. What are we not thinking about? What are some of the barriers that we're not considering? Whatever sequence we do this in, this is a lot of build out. What are barriers that we need to be thinking about as we grow to this scale?
What are we not thinking about? Well, I think we could cover, energy, certainly we're being mindful of, right? I think that, I don't know if that problem has been fully appreciated, particularly as other decarbonization strategies are all pulling renewable electrons in the grid. I'm concerned that there's too much emphasis on electrification, renewable energy to solve the problem of direct air capture, and that we need to be clever, particularly when you think about land usage, resource usage, and siting in kind of the geographical context, that we're being very intentional about how we're pairing these technologies. I think the equitable distribution of benefits from direct air capture, let's just call it what it is. I think industrial progress has not historically considered these. We have an opportunity to right that ship. I think we have an opportunity for regulatory bodies and government to kind of insist that you have social and environmental impact assessments in hand, and that you're communicating these to communities and engaging them robustly and in an auditable fashion right off the bat. One of the things I think we do miss, though, again, when we think about that scale, is that it's not necessarily what's economically or technically achievable that sets, I think, that upper bound for what we can do with with direct air capture. It's how do we can progress through these sort of tiers of in the supply chain and other when I think about the impacts that we see at scale. One of my favorite studies is the power of place, that looks at land by by that classification by tier. And what you'll find is that as you scale, you kind of hit different tiers of harm, right? And that's where I think we're missing in the conversation. So where do we really stress that supply chain to the point where we do have to start compromising on harms to communities? And I'll maybe leave it there.
And Peter, you've talked about this a lot, about the opportunity for, your vision or scaling DAC more generally to be positive, create positive equity, to not reinforce inequities. Can you say a little bit more about that?
So the previous Industrial Revolution had the inequity of the fact that the natural resources were in the developing world and the technology was in the so-called developed world at that time, and that the bulk of the wealth generated went to the technology providers. And so we cannot repeat that before, even if, let's say, the U.S. and other countries are the technology developers, the REMI, the economy, the DAC-based economy, can be implemented in those countries and can be practiced in those countries. But most importantly, one has to transfer the capability for them to make it locally, to create the jobs in each of those countries to do it locally. One has to follow in some sort of version of what Salk did with the polio vaccine and make sure that in some form DAC is either open source or at least minimal royalty based to the people who spend a lot of money and investing in it and creating it, but certainly not have any barrier to entry. Every company in this space should have its single goal to maximize the implementation rate. Right? Now, one other thing I want to say, what Pete has pointed out, which are all well thought out ideas. I'm not saying that the path doesn't have its challenges, but I can assure you, and we don't have the time to do this, that energy usage or land usage or cost will not be one of them. For some of the things that Klaus has said about how, as we traditionally have scaled up, costs have gone down, and so the cost will not be a problem. The energy efficiency will be part of those costs going down, and will be less energy used. And most importantly, we have to make a distinguishing feature in our discussion about energy between primary energy production, which is electricity, and heat energy production, right? At least our technology at Global Thermostat is based on 80 to 90% low temperature heat and minimal amount of primary energy production. And so it's a cogeneration technology. And finally, in making valuable products, you're also generating heat as they come together, and they bind and create new products. Those processes are inevitably exothermic, and so they get heat as well. So there's going to be plenty of heat, and when people talk about the pressure on the energy demand, right, and I agree with what Klaus said about liquid fuels 100%, that in addition, they should recognize that one can co-generate with electricity production if we use as sources concentrated solar, nuclear, geothermal, all those sources simultaneously produce, and nuclear, simultaneously produce primary energy, electricity, and heat.
Thank you. Klaus, can I turn it to you for a second? And I actually wanted to touch a little bit on your point around the importance of modularity in achieving scale. Is there something in the way that we are currently funding and conceiving of building out direct air capture right now that feels suboptimal in terms of the modular approach that you think is necessary in order to drive down costs?
I do think that there's a point there. The problem we have there, it's a little bit like the drunk looking for the key under the light, even though it's somewhere in the dark. And we know pretty darn well there are learning curves and learning rates, and I can simplify the problem by saying there are two things. There's the learning rate, and there's the irreducible cost below which you will not get. And for photovoltaics, that irreducible cost is very low, so they could come down by nearly a factor 200 since it all started. Now, direct air capture has an irreducible cost too. We don't really know where it is, but I'm hard-pressed to get to more than a few tens of dollars. If I simply add up the minimum energy requirement, that seems to dominate the cost. If I'm saying the sorbent has a certain cost, then I multiply this with 3 or 4 for having the rest of the stuff. $30 is probably above the irreducible cost. But we don't know these things. We are very uncertain. And I can tell you one thing. If we have a 10% learning rate or a 20% learning rate, makes a huge difference. Statistically, we know that things which are big have a low learning rate. Highly modular things have a very high one. One of the most extreme is photovoltaics at 24%. I would argue the difference between wind and solar could very well be explained that wind spent the last 20, 30 years trying to get bigger and bigger and push the limit that way rather than mass produce, and they had a good reason to do that. I'm not arguing against it, but I'm pointing out they came out at a 15% learning rate, and the difference between 20% is you need to grow 1,000-fold to get a factor 10. If you are at 16%, you need to grow 10,000-fold, and if you are at 13%, you need to grow 100,000-fold before you learn a factor 10. So we should spend some time figuring out what technology choices we make and how they might influence these numbers. And I am the first one to agree that we neither understand irreducible costs all that well, nor do we understand the cause of learning rates. And I take that word with a caveat. This may not be learning in all of its details. It has a very complicated backdrop, but there is an experience curve which says the more you deploy it, the cheaper it gets. And since we don't fully understand it, we tend to ignore it, and I think that's a mistake.
I think I'll add, I think maybe the panel's in somewhat agreement of where we think those DAC costs will get to. Maybe rest a little bit on the higher side, $150, $100 per ton. The two concerns with learning rates, one, well, maybe three, you're using proxy industries, right, to drive this down. And a singular learning rate falls a little bit on its face versus a kind of component learning rate, particularly because I think one of the ways in the doors to reduce risk for early DAC is to bring in mature components that have already gone down those learning curves. The second is, I think it's kind of the hybrid method that you really have to be very careful about how you are pricing that first of a kind plant, right? So do a kind of true bottom up analysis where you start and then kind of taking that down the curve. And I think where you find a lot of differences in the cost estimates in the literature kind of surround those 2 points.
Great.
But let me make one more point on the total energy consumption. I used to say this a long time ago. We have fossil energy. There are 3 things we need to do. We need to extract it, we pay for that. We need to convert it, we pay for that. And we need to clean up after ourselves, and we forget about that. Right? That will cost you energy, and I wouldn't be surprised if at the end that's a 20-30% extra energy consumption we will have to pay. And that's part of the deal if we need to clean up. And by the way, if we forego fossil energy, we will have to get that energy from somewhere else too. And we picked fossil energy because it was so efficient at doing things. So we will have a higher primary energy consumption as the world moves through it, unless we do some clever bookkeeping. But overall, we have to pay for what we are doing, and we will, as a society, one way or another, do that.
Peter, I'll give you the final word here.
Right. So look, as far as cost is concerned, right, the National Academy in a 2018 study said that cost could go as low as $25 a ton, right? I believe the costs can go certainly under $50 a ton, right? And as far as learning rate is concerned, I think if we're going to meet this challenge, just think about the whole world, all the technical contributions surrounding this area of addressing climate change. Think of the scope of that. Think how many talented people will be learning and contributing their expertise to it. This is not a normal approach, right? I think the learning rates, if you try to figure out what the learning rate was during the 1 year of Los Alamos it'd be amazing, right? And so we got to be careful when we use past metaphors to deal with this unprecedented threat we face. Yet we have the capability to do it, and really it's up to us. We just have to decide to do it, in my opinion.
Both of us are old enough to know that in the case of photovoltaics, to stick with the analogy, people say it can't keep going like that. Moore's law ended in 1990 and it's still going, right? So ingenuity will change things, and it will change it in increments which you cannot understand at the beginning. Put yourself in the mindset of a 1970 engineer working on photovoltaic, and you tell him, I came from the future. I know that 99.5 cents of your costs are gone. Now, please explain to me what that last half cent still is. They couldn't possibly do it, right? So you have to rely on the fact that this is a very complicated story which is done in increments and step by step. And I would point out that in solar specifically, you still talk about the very same technology. It's not that there was a revolution which completely changed how we do things.
Wonderful. Thank you so much for the rich discussion, everybody. Can we give our panel a round of applause? Thank you so much.